Jeff McAlvay with Tempo Automation. Before working at Tempo, I used to work at an industrial supply company called McAlvay. So they do distribute about 500,000 different parts. And it was over in that context that I was really excited about the prospect of having a way to quickly iterate through the electronics designs, and that's how we got going with Tempo. And I'll talk a little bit more about it later in the presentation. But the focus for today is really about what are some of the principles and a sort of framework for thinking about the electronics development process. And just so I can tailor my comments, I'd be curious to hear just a show of hands in terms of how many folks are electrical engineers, either by formal training or by something they enjoy doing. Okay. How about mechanical? Software? Great, really good mix of folks. Business side of things? There it is. All right, wonderful. I guess with that in mind, when you're trying to sort of develop a new product, there's just a lot of different sides of it to be able to keep track of. I mean, I think these are just some of the examples of many. So the experience in industrial designs, how should the software work, how do you integrate the different systems, how do you make sure that you're designed for test properly. In the context of this talk, I'm going to really narrow down on a couple of them: product design, mechanical design, electronics, and EMI. And so I think the overarching theme of the talk is really around the way that I think about prototyping as risk mitigation. And bringing a product to market, there's a lot of things that can go wrong. It's like, oh, your board doesn't fit in the box, or it doesn't work with the software, or it interferes with other products. The way that I like to think about and approach prototyping is how do you eliminate each of those risks in a very systematic and methodical kind of way. And so the first is to do with mechanical design and things that go wrong when you're thinking about your electronics prototype in the context of the mechanical design of a product. And I think one of the overarching principles here is just the importance of having a really tight interface between the electronic side of a project and the mechanical side. It's very easy for them to sort of walk out of sync, and all of a sudden, at the last minute, it's like, oh yeah, this board should fit in this box. And everyone's like, uh-oh. And this is not a good situation for anyone. And so one of the fortunate things about digitally making sure that things integrate well is the existence of these file types that oftentimes can be handed off between both the mechanical and the electrical CAD tools. And so I think of, like, for example, like SolidWorks and Altium have a very good integration when it comes to those functions. I think one of the just sort of some Ecke 101 type of notions that if you spend more time on the electronic side might be non-obvious is it's very easy to sort of design your board in such a way that the mounting of it is over-constrained. And one of the notions of having tolerances on holes for a product is that if the tolerances line up such you have things out of sync, then very easily you're in a situation where all of a sudden you can't install a board into the screws or whatever mounting device you were hoping for. And so one way that you can prevent that over-constraint is the introduction of a slot as a way to give you a little play along a given dimension. And so at this point, I guess I wanted to introduce just sort of a couple of three mental sets and frameworks to sort of think about how to make the electronics design compatible with different facets of the mechanical purpose. And so one of my friends who I was getting feedback on with this talk, I used to work at HP, and when they would one of the considerations in terms of the size of the board and the printer would go into how big, how many printers could they fit in a big truck, like a 53-footer. And that was sort of one of the considerations. If you say, okay, how big's the board, how big's the printer, how big's the package, how big is the carton that contains it, the pallet, how many pallets can you fit in a big 53-footer, and so that's sort of the outside-in perspective in terms of those containers are really the unit of shipping and delivery. And so thinking about that dimension as one dimension for analyzing and thinking about your design. Another way is more of sort of an inside-out direction. And so one of the things to really appreciate about the electronics manufacturing process is the extent to which that many of the fabricators who are involved with manufacturing circuit boards are really built around these 16 by 22 inch panels. And so all the equipment and process and tooling is set up to go and support those type of panels. And so that implies some thoughts around how to design your board such that it supports those processes well. And so you can imagine if your board was 8.1 inches by 11.1 inches, all of a sudden you're only able to fit one board on the panel. Whereas if you sort of find a way to shrink it down a little bit, then all of a sudden you're able to fit four. And so it just, that holds true for smaller and smaller versions of the board. And so design for this notion of panelization is another important consideration. And a third, and somewhat obviously, is to do with your application. And so this is oftentimes working with the industrial designer on your team, and really thinking about a form factor as to wearable that's going to be comfortable, or some Internet of Things device that needs to go and fit in this particular place and needs to look like this. And so very naturally, there's sort of a tight interaction with industrial design, mechanical engineering, sort of something that's going to be a delightful experience for the user. So all this to say, that when it comes to designing your board, three sort of considerations to think about are sort of one is sort of the design for containerization, design for panelization, and then design for the application that you're going to be working towards. And so that was that summary. And so I guess with that in mind, one of the things that you can do to go and support that process is, and this gets into sort of a wider challenge to do with a lot of these projects that involve multidisciplinary undertakings. And so, interesting to hear like a lot of software, a lot of mechanical, a lot of electrical here. It'd be kind of nice if everybody could sort of go off in their own direction in isolation, and then it just magically comes together at the end. Sadly, it's not so easy. And so, as an electrical engineer, there's a degree to which it's your responsibility to go and find a way to do what you can early on to go and give your team members sort of a sense of what it's going to be looking like and what they can expect from you. And one of the challenges, given that time is a constraint, is with some creativity you can think about ways to do that that don't take an enormous amount of time on your part. And so thus this concept of mechanical mock-up. And so this is a notion, and so this is very explicitly a non-functioning board. It's not going to behave electrically how you want. If you try to load firmware, there's maybe no chip to even receive it. This is really a notion of like, hey, here's a board you can hand off to the mechanical guy, say like, hey, is that going to, or guy or gal, is that something that's going to fit in the enclosure that you want to have them put it in? And so you could include things like just sort of resistors to give a sense of what the heat that's going to come off the thing. You can sort of have some weights to give a sense of like the feel for it. You can sort of buy those from various different places, little weight things you can go and add to it. Sort of figure out the batteries, how that's going to fit. The LEDs, are the ones that you chose going to light up the way you like? Are the connectors going to work? Can you fit all the different connectors on the board how you want? And further, I think that maybe the only like live components that are really crucial to add are the ones that you know are going to be very tall, whether it's like big electrolytic caps or various other components that have a potential to interfere with other various parts of your mechanical part of the process. And so if you do this, oftentimes your mechanical engineer will be very appreciative insofar as you don't have unwelcome surprises late in the process where the integration test comes in. It's like, oh, there's no way this is going to fit. And oftentimes as an electrical engineer, you're the unlucky party of trying to find a way to cram it in to the form factor that industrial design is specified. And so by doing this, you can sort of set expectations in terms of what's going to happen. I think one blunder that can come with this pattern is making sure you're deliberate about the solder mask color for the board. I think in my experience it helps a lot to have a different solder mask color for these type of prototype fake ones. So it isn't like, oh, this is out in the field, it's like, oh, we're trying to put this together for a prototype to send out to customers. It's like, oh, it doesn't quite work. And so to have it just glaringly obvious, like what isn't real, I think is definitely a value. Final comment, I guess, sort of in light of recent events, sort of a lot of exploding Samsung notes or whatever they are. I think one of the principles that is behind a lot of challenges they had is that I think of it as being a problem that was due to a failure of the interface between electrical and mechanical. Insofar as the way the design was done, it compressed on the battery in a way that the battery was not appreciative of, and to put it kindly. And so I think it's something where, like in some of them, it didn't cause problems, but enough of them that compression caused some real trouble, and nothing like. No good marketing like at the beginning of every flight saying if you have this phone, you're going to get kicked off the plane. And so, anyway, so just be particularly wary about the clearances of batteries is all that is to say. So, in addition to some of the other things that you can validate that I mentioned before with this type of a mock-up is sort of connectors and cables. I think one of the fun things, particularly when you get into sort of wearables or devices that have many different boards that are hooked together, is just routing the cables and the connectors. It can be an afterthought, but oftentimes are very sad when it is. Make sure it mounts to everything, all the circuit, all the sort of power supply, batteries, all that type of stuff work. And I guess we can cover some of this other stuff. So that was basically a way that you can sort of set up the interface between the electrical and the mechanical engineer for success. And now I guess I want to talk a little bit about what it looks like to set up the software team for success from the electronics design perspective. And so I think, so here again, you're sort of putting yourself in the mindset of what would a software engineer in your team most value? What do they want to sort of interact with and see and work on? And so I think there's value to having another board that, in the context of this one, the form factor doesn't really matter. It doesn't need to fit in a particular box or containers or designed for fitting in a tractor trailer or anything. It's more like, hey, what's your software engineer going to enjoy having on their desk, and sort of loading version after version after version of firmware on, hoping that it works. And so just sort of a couple of considerations and principles to make this a really nice layout for them. I think it's nice if just all the cables sort of come out the back so they can plug it into the various things there instead of having to like reach around their keyboard to try and go and get their hands on it. I think further, just having really nice grounds and just tons of LEDs so they can see, oh, this GPIO's on, or hey, we got power, or all these different things. Otherwise, it's sort of like, oh, we have to sort of load it up and do all these different things. And it just, the more that you have that instant gratification of like, oh, the hardware is working, why is my software working? That validation is really helpful for folks to have. And nice to be able to just like reset and it's like, oh, I did it wrong. And it's nice to just press a button instead of have to go like refresh firmware and things like that. A couple of other comments on it. So it's nice to have the programming port broken out naturally and sort of having that populated. Testing and debugging connectors, test points galore. If you like, if it sounds like a software guy says, hey, it's not working, they'll hand it to you and sort of, you can poke it and sort of figure out why that's the case. Okay, so that was that. And then if you're feeling like you want to make it a really luxurious experience for your software engineer, you can do a mounting plate, so instead of having it just rest loosely on the table. Okay, so we talked about those things. So I think, so we talked about sort of design to support your mechanical team, design to support your software team. I think another set of considerations that I think was being important when you think about electronics design is designing and thinking about electromagnetic interference. And this is one that is sometimes not intuitive and can be overlooked until in a project, which is often to very negative results. So just sort of really quick principle to think about here is this notion of the currents are going to be flowing in a way that's going to minimize the area for them to travel. And so an implication of this is you want to be a situation where every time you have a signal, you have a ground that's close to it. And so larger, if there's a big space between the signal and the ground, you're creating all this electromagnetic interference and setting yourself up for trouble. And so a couple of reasons why it's worth caring about that as a potential problem. So one is just the product screws itself up. And so it could be something where it's like, hey, I expect my radio to be able to sort of have this range, and all of a sudden it's not. Why not? Oh, it's because something else on the board is messing it up. Or maybe you have sort of audio as a component of the device, and all of a sudden there's all weird noises over it. It's like, oh, why is that? Well, it's because of the way that you designed the board, it wasn't compatible with minimizing EMI. I think another problem, and this is bigger, you get in trouble with folks like the FCC, is if your product is one that would interfere with other products. And so the FCC is just not going to pass you if all of a sudden any cell phone near you is not going to work. So just take an extreme example of it. And then further, I think there's wariness about wanting to be a situation where you want to make sure that other devices nearby aren't going to cause it to break. And so if somebody has a cell phone, it shouldn't cause your product to break. And so specifically, what can you do to go and prevent these outcomes? So I think, again, these are just instances to reinforce the principle of trying to minimize that distance between the signal and the ground. And so one genre that we see a lot is around, so if you have this big slot in the ground plane, and then sort of a trace that runs over it, all of a sudden you have this big loop that becomes sort of an antenna as the current flows around it. And so the sort of natural thing to do then is how do you sort of maybe have a little gap in the slot that makes it so that you can have the ground return and a much tighter loop. Similar principle applies to cables of when you're thinking about what are the signals you want to send across different aspects of this cable. It may be at first glance, oh yeah, I'll put power over here and ground over there, but all of a sudden, like you have this big loop going on again. And so again, sort of to put the principle in play, put the power and ground on the ribbon cable together, and all of a sudden you have a much tighter one. And so, in general, there's this notion of, you can think about it in the context of traces. So instead of cables, you can imagine traces. And in general, I think it's a good practice to take this pattern, signal, ground, signal, signal, ground, signal. Insofar as every single one of the grounds does have a neighboring signal, but you don't have to go so frequently as to be signal, ground, signal, ground, signal, ground. It's just a way to get a little bit more space between the two. And so in addition to sort of along the XY dimension of the board, along traces or ribbon cables, you can also imagine Z across different layers of the stack up of your board. And so again, the best practices here are around the notion of signal, ground, signal, signal, ground, but always having a neighbor that can go and return the current. So I guess to just sort of summarize here, the big principles are really putting yourself in the shoes of the mechanical engineer, of the software engineer on your team, and really thinking about how can you design versions of your board that aren't going to be mammoth sucks on your time, but are going to still give them a sense as to what to expect from you. And it's going to make their life easier and really prevent this situation where you run into trouble when it's time to integrate everything and things just don't fit together and everybody's grumpy about it. And further, this last section of it was just really about thinking about EMI and just being cognizant of its existence and be able to sort of do some quick and easy things that hopefully control it. I think there could be tomes written about it, but keeping these principles in mind hopefully will keep you out of some of the worst offending issues. So just a word or two about us. We have an electronics manufacturing factory over in the Dogpatch neighborhood of San Francisco, and it's really purpose-built for low-volume electronics manufacturing. And one of the things that we're really proud of investing very heavily in is the software involved with coordinating our factory. And so software involved with automating the quoting process, software involved with coordinating the supply chain, software involved with running the factory, and we've really been pleased by the extent to which it's cut down the time that folks are waiting for quotes, it's cut down the time and the possibility of errors and issues arising in the process, insofar as it's the data running all the way through. And so the culmination of this process is that for most boards, up to 8 layers, we'll find the board, find the components, assemble them, test them, deliver in the span of 3 days. And a lot of people, when they're trying to sort of validate these things very quickly, find value in being able to sort of do that rapid iteration to go and do those type of checks. So happy to talk more about that if you have questions. I guess that's what I wanted to cover.